Okay, good afternoon, good evening, whatever it is, wherever you are. We're back to our normal lecture format. And today we're going to be talking about actually one of the most important aspects of the environment and ecology, and that is the air which we breathe. Now, we're going to be talking mainly about air pollution. I'll tell you a little bit about the structure of the atmosphere, etc. But in this discussion of air pollution, we are going to leave out, for the most part, the most important pollutant of all, and that is carbon dioxide. And that is because we've already had an entire class on global warming, on the effects of carbon dioxide pollution in the air. But please bear that in mind all the way through. The most important pollutant of all for modern times is carbon dioxide. But we need to talk about all the other pollutants as well, as you will see. Okay, so let's have a look, first of all, at the air that we breathe. Well, we breathe air for a specific reason, and that is we are aerobic organisms. That is, we depend upon oxygen. We depend upon oxygen because we use it to burn the fuels which our body stores. For example, sugars, fats, all of these things are actually fuels. And we effectively burn them with oxygen, and we extract energy in a metabolically useful form in order to drive our metabolic processes. Everything that we do, movement, speech, whatever, all of these things require energy. And that metabolic energy is derived from fuels, which put together with oxygen, and energy is extracted from them with the result that we actually produce carbon dioxide. So we have to breathe in to get the oxygen into our lungs and into our bodies. We breathe out so that we breathe out the waste carbon dioxide. The air that we breathe, in fact, is composed mostly of nitrogen. So the vast majority of the gas in the atmosphere is nitrogen, 78%. And that does nothing for us. We breathe it in, we breathe it out. It does nothing. It's effectively inert as far as we are concerned. Oxygen is about 21%. And remember, the origins of that oxygen is all from photosynthetic processes by organisms that can photosynthesize. Carbon dioxide, in fact, is quite a very low percentage in the atmosphere. It's only 0.04%. And you'll realize that with such a low percentage, when we add carbon dioxide to the atmosphere, we can actually make a tremendous difference to the effects of carbon dioxide. That's why we see these global effects in global climate change. Now, in addition to that, there's water vapor, there's other things, nitrogen dioxide, various other gases, but they are minor compared to these three major components here. So these gases exist in the atmosphere, and the atmosphere has a particular structure. I'm not going to go into much detail about it. There are two areas in particular that I want to talk about. The first is called the troposphere, or the troposphere. And that is up to about 10 to 12 miles high. And this is the area where most of the gases of the atmosphere are contained. The 70 to 80% is present here. And that, of course, is the part of the atmosphere that we live in, closest to the Earth. And that's what we breathe the air from, the troposphere. Once you get to the top of the troposphere, the amount of gas present is very low. If you were to measure the amount of gas, there's the easy way to do it, and that is to look at the pressure which the weight of air actually creates. And if we were to do that, we'd find the atmospheric pressure is greatest here, close to the surface, obviously, and decreases quite rapidly as we ascend. We reach a point here where actually the atmospheric pressure is extremely low. And this is an area called the stratosphere. And the stratosphere is also, for the most part, extremely cold. In general, as we ascend, the temperature will fall as we go up. The stratosphere is the next layer to the troposphere. when you fly a long distance, especially if you fly an international flight, you actually fly in the bottom part of the stratosphere, about between 10 and 12 miles. And there's a very important feature of this boundary between the troposphere and the stratosphere. And that is there is a thick layer here of a gas called ozone. And ozone is O3. It's an oxygen molecule, but there are 3 oxygen atoms joined together to form the molecule. And we'll talk more about that. But the ozone layer that you've probably heard about. Oh, what are you doing? The ozone layer that you have probably heard about. This is it here. And the ozone layer lies at right at that boundary between the stratosphere and the troposphere. So we actually have very little choice. This is one of the things about air pollution, about pollutants in general. We have to breathe. We have to get oxygen into our lungs as best we can. And there's very little filtering mechanisms that take place apart from things like the nose that will filter out large dust particles and larger particles. The nose also has a layer of mucus lining it, which traps material. And this is when we blow our nose, that's what you're blowing out. You're blowing out mucus that contains dust and particles which have been trapped by the nose. But the nose has no ability to filter gas, to distinguish between different gases that it's taking in. It can only take out solid particles. So, and those are taken out by the nose. It's quite efficient at removing particles, but it cannot remove very fine particles. And those may be inhaled into the rest of the respiratory system. Now, the rest of the respiratory system below the throat is guarded by a system of mucus, which is moved continuously by cells which have little hairs on them that beat, and they continuously beat in an upward direction rather, and they shift a sheet of mucus continuously from the lungs all the way up to the top of the throat, where it is swallowed or spat out, but usually it's, for the most part, it is swallowed. And this is quite efficient at filtering out material down to the size of bacteria, for example, which are very small. And they get trapped in this mucus and then removed. But there is a great problem with very, very fine particles. And this we're going to see increasingly as we talk about air pollution. We're going to see that these very fine particles are a particular problem because they can end up being taken into the deepest recesses of the lungs, to these little sacs called the alveoli, which is where gas exchange takes place. That's where we exchange our oxygen and our carbon dioxide. If those very fine particles end up in the alveoli do not have a very efficient cleaning mechanism to get rid of them. And those particles may accumulate in the alveoli. They may even enter the bloodstream. And this can cause severe problems, especially if it's done over a long period of time. So the other thing is, of course, as I said already, for the nose, it doesn't screen out what kinds of gases. If we are breathing air with toxic gases, we will end up breathing those toxic gases into the very deepest recesses of the lungs and absorb them and then distribute them through the body. So when I say that we have little choice, when we are presented with polluted air, we will realize that the polluted air may be containing 2 things. That is, it may contain particles, which are potentially noxious, and it may contain gases, which are toxic to us. And because we are driven to breathe the whole time, we may in fact be forced to take in some of those toxins along with the oxygen which we require. So there are particular things, particular responses of the body to the presence of things that we would consider pollutants. Now, a pollutant is really anything which does not occur as a matter of course in the air, and especially those things which have the potential to cause harm to whatever breathes them or whatever is in contact with them. So for us, there are some particular health responses which are really important. The first is that many of the pollutants that we breathe in air which is polluted will cause irritation of the lungs, inflammation of the lungs, and this is dangerous even to people with healthy lungs. The air pollution can reach levels where even healthy people begin to be severely affected. But if this is happening, for example, to somebody who already has a lung disease, already suffers from asthma, for example, or chronic obstructive pulmonary disorders, COPD, or any of those things, they can be exacerbated by taking in these toxins. And it may, in fact, be that the effect of the pollutant is actually redoubled if the people already have some lung disorder. So lung tissue, lung swelling, lung irritations, these have a multitude of effects, and they can and frequently are fatal. And in addition, in young children, it may affect the development of the lungs, which predisposes them then to lung disorders later in life. The second thing is we know that air pollutants can, in fact, have a direct effect on cardiovascular function, the function of the heart in conjunction with the vasculature which feeds into the lungs. And air pollution increases the risk both of heart attacks and of stroke. In addition, in areas where air pollution is constant, where it is a chronic problem, we notice that mothers tend to give birth to infants with low birth weight. And this increases the risks of infant mortality, but it also affects later development. And because of low birth weight, for example, we know that low infant birth weights are associated with developmental problems later. Overall, air pollution is one of the major causes of premature death in the human population. And it is a very, very important area of environmental attention worldwide. And for example, United Nations, the World Health Organization, many different organizations devote a tremendous amount of attention to air pollution because of its widespread nature and because of the very direct health effects that it causes. So how many people actually die of air pollution? Well, do people die? Yes, they do. They very, very definitely do die. And a lot of people die. In fact, it's estimated that about 7 to 8 million people a year die as a direct result of air pollution. And that's comparable to the number of people who die because of tobacco smoking, which, if you think about it, is simply voluntary air pollution. Because if you're smoking, you're taking in many of the same compounds that we associate with badly polluted air, as you'll hear in a while. So there are two things which contribute to air pollution, which cause the maximum amount of damage, I've already mentioned. First of all, particulate matter. We need to examine that a little bit more. The first thing is that particulate matter is very often derived from partially combusted carbon compounds, either solid things like coal, wood, or else oil, other fossil fuels. These are also carbon-based. And when you burn them, they very often are not burned completely. They release particles of partially burned compounds. And those are not just carbon. The carbon on its own as a very fine particle is itself dangerous if it's taken down deep into the lungs. But very often associated with these small particles, there are toxic carbon compounds. of various kinds of tars, for example, those sorts of things, which themselves may be extremely damaging, even carcinogenic. Second of all, the second major component of air pollution are toxic gases. For example, carbon dioxide, we've already mentioned, carbon monoxide, ozone, we'll talk about a bit more as a dangerous gas. Very commonly, a compound called sulfur dioxide. And sulfur dioxide is particularly dangerous because it combines with water vapor to form small droplets of sulfuric acid, which can be inhaled, but which can also cause widespread ecological damage. Then there are a whole lot of oxides of nitrogen, nitrous oxide, nitrogen dioxide, various other things. You'll often see these lumped together into a group called NOx, NOx, NOx. That just means oxides of nitrogen. They have a particular effect, which we'll discuss later on. Then methane, and these, very importantly, this is a name you need to remember, volatile organic compounds, or VOC. To explain VOC, I'd say if you were to open a can of paint, just imagine opening a can of paint, what you smell. Immediately you open it, you smell something. You don't see anything, you smell something. That is a set of gases. They're mostly organic compounds, which are very volatile. That's why you immediately smell them. And those would be typical volatile organic compounds, things like solvents. All of those sorts of things, those are volatile organic compounds. But they are volatile organic compounds are also released as pollutants from the process of burning coal, for example, or oil. Some of them are really noxious. This one, formaldehyde, that's what you preserve bodies with. It's a very nasty substance. Okay, so where do we get this? Well, first of all, we need to recognize that we class air pollution into two broad groups. The first is indoor pollution. And indoor pollution is particularly dangerous because it is contained. It's there almost constantly. It's very difficult to avoid it. At least if you're outside, then the air pollution tends to become dissipated. It becomes diluted by all of the other air. But if we're inside and there is a pollutant, that pollutant doesn't move. You're constantly exposed to it. And you may be exposed to it in very low concentrations over a very long time, which has a cumulative effect. We need to spend just a minute looking at our own homes and realizing that there are a multitude of pollutants inside a home. For example, new carpets, new upholstery, in textiles, synthetic textiles especially, produce gas. We say they outgas, and they outgas volatile organic compounds, which can be extremely dangerous in high quantities, but in low quantities, you may not notice them. But if you're exposed to them over a long period of time, they may well have an effect. We voluntarily expose ourselves to things like solvents, paints, different solvents of those kinds, and involuntarily to things like the outgassing from upholstery and everything. But there are many other things which we use inside the home, which actually produce air pollutants that we don't even think about until it's pointed out to us. For example, it is still common throughout the world for people to have fireplaces inside their homes and to burn wood, for example, or coal. These, even a well-vented fireplace, will produce pollutants which will enter the home. And those will be both particulate and gaseous. A particular concern for many health experts in developed countries are things like candles. A candle is nothing more than a solid block of hydrocarbon. That's what it is. It's a fuel. And when you light the candle, you volatilize the fuel, and that gives you the flame. But at the same time, it produces a whole lot of waste products, VOC, but many other things as well. And candles can be actually a major source of indoor pollution. You need to be very careful in using them. We use spray cans the whole time. What is in the spray can that propels material out? It's very often a propellant of some sort. It's a gas which has been compressed into the can, which you then release. Well, what is that propellant? It may well be a pollutant with potential danger. All sorts of cleaners that we use, the household cleaners, kitchen cleaners, those things that promise you that your bathtub is going to be whiter than any of your neighbor's bathtubs. All of these sorts of things. Have a look at the bottle. Look at the contents of the bottle, and you'll realize that they potentially are adding to the pollution burden within the home. And there's all sorts of things that we do voluntarily. We barbecue, we burn coal, we burn wood, we burn coke, all of these sorts of things as almost as a sort of form of entertainment, but they expose us to pollutants. And all of these things are cumulative. We are continually bathing ourselves in these pollutants, and they may well have an effect if you're sensible about them, and then you can avoid risks. So here's a particular one which really did relate to domestic use. And just for a minute, I've got to go back to our discussion about the ozone layer. The ozone layer lies, as I told you, between the troposphere and the stratosphere. It's quite a thick band. It's anything up to 20 miles thick. And it has a high concentration of ozone. And ozone is the oxygen molecule O3. Now, normally oxygen exists as O2, but up in the upper layers of the troposphere and in the lower layers of the stratosphere, the sun's rays, which are composed of light, heat, and ultraviolet light, hitting on the oxygen molecules in the atmosphere, breaks them, and it causes them to reform as this form, O3 instead of O2. Here's O2, here is O3, ozone. Now, up in that, contained in that layer, it's extremely useful to us because the ozone layer actually absorbs ultraviolet light, and it absorbs about 95% of the ultraviolet light from the sun. And that ultraviolet light is extremely damaging to biological systems. If you've lain out in the sun too long and got a sunburn, you have a very mild taste of the kind of damage that ultraviolet light can do to you. Without that ozone layer, life on Earth in terrestrial environments would not be able to exist. It would be able to exist in water. But without the ozone layer, all life would have to be under the water because that's the only way you'd be able to screen out enough ultraviolet light to survive. So it's extremely useful to us. Now, here's the problem. That was for much of the middle half of the 20th century. We were using a prodigious amount of compounds which were able to actually break down ozone. And these were, the sources of these were industrial, certainly, but also domestic. And we were using compounds, first of all, as propellants in cans of sprays of all sorts of different things. But they were also widely used in refrigeration as refrigerants, and for an important reason. That is that these compounds were easily compressed and liquefied. And if you then lift the pressure, these compounds evaporate, turn to gas again, and cool. They become cold. As they evaporate, they become cold. So we could use them as refrigerants. And if ever you've sprayed a can, maybe you a can of air, compressed air, you know if you spray the can for a long time, the can gets cold. That property was used to drive refrigeration. But unfortunately, refrigerators have a lifespan. And at the end of the lifespan, even during it, they leaked those propellants. And they were used to be of two major forms. The one class were chlorofluorocarbons, and the other were hydrochlorofluorocarbons. And they've complicated chemicals, but what's really important is this chlorofluoro part, chlorofluoro. Those are a group of elements like chlorine, for example, and fluorine. These parts of these molecules have the ability to actually destroy ozone, to reduce it to its O2 or O form. So they actually break down ozone. Here's the real problem. These were so widely used that they began to accumulate in the atmosphere as pollutants. But they are extremely long-lived. Some of them are, the lifespan is like 700 years. And they begin to drift through the atmosphere. They actually accumulated right at the top of the troposphere and the boundary of the stratosphere, close to and into the ozone layer, where they began to break down the ozone. And they not only do they break down the ozone, they're very long-lived. Second of all, a single molecule can break down hundreds of thousands of ozone molecules before it itself is broken down. So they were extremely potent at breaking up the ozone layer. And this began to be so bad that, in fact, the ozone layer began to disappear in certain parts of the globe and began to weaken in much of the globe. So, for example, there's a famous ozone hole. Here it is here, this clear area here over Antarctica was the most well characterized. But the weakening of the ozone layer extended far further. Now, I have to tell you, this picture was taken about 5 years ago. And this ozone has actually strengthened tremendously since then. The ozone weakening extended over much of Africa, South America, Australia. And then there's an Arctic ozone weakening as well, which extended over Europe. And this began to be well characterized because people noticed that the amount of ultraviolet light hitting the Earth was increasing. And there was tremendous concern about the health effects because the ultraviolet light can cause all sorts of things. It causes cataracts. It causes effectively constant sunburn, which results in skin cancers and all sorts of other effects as well. And in 1987, a treaty called the Montreal Treaty was signed by many of the nations of the world, agreeing to phase out those compounds, the chlorofluorocarbons, hydrofluorocarbons, reduce them. They're all classed as CFCs, chlorofluorocarbons, phase out CFCs and replace them with compounds which would not damage the ozone layer. So this was actually a tremendous success story. This is one of the success stories in ecological activism, that the damage to the ozone layer began to be repaired naturally by the Earth systems as soon as we lifted those pollutants from the atmosphere. And there are very marked signs of this healing, and the Arctic is predicted to return to normal by 2045, Antarctic by 2066, but there's already substantial improvement. So yes, that is a success story. Not so much of a success story are other aspects of indoor pollution. More than 3 billion people worldwide use open fires for cooking and for heating as well. And more than 3 billion people. Out of those 3 billion, there are up to 4 million deaths a year directly attributable to inhalation of pollutants from these cooking and heating methods. As soon as people start to use biomass, that is wood, cow pats, which is commonly used to be burned for cooking and heating, peat, charcoal, all of these carbon-rich compounds, when they're used for cooking and heating indoors, actually, even if they're used outdoors as well, they produce, as you realize, they produce a tremendous amount of smoke. And the smoke itself is actually toxic. What you see when you are looking at smoke plume is a whole mass of partially burned carbon compounds mixed with all sorts of other gases. First of all, typical for this kind of air pollution, the toxic particles of partially burned substances with all the tars and everything else associated with them. Gases like carbon monoxide, sulfate, which is that sulfur dioxide, which together with water forms sulfuric acid. Just imagine if you are breathing in sulfur dioxide, what does it do? It dissolves in the liquids of the lungs and it forms sulfuric acid. It reduces the pH of your lungs and is extremely irritant. Wood fires, biomass fires also produce copious amounts of volatile organic compounds and all sorts of other things. One of the major problems of releasing things like nitrous oxide, nitrates, those sort of things, we'll see in a little while, is that this increases levels of ozone. And ozone at our level, where we can breathe it in, is dangerous because ozone is actually extremely irritant. I'll talk a little bit more about that in a while. All of this results in a whole range of different respiratory and cardiovascular diseases. And it also goes so far as causing immune damage and eye diseases, those sorts of things. But are particularly at risk are women, because they're the ones, first of all, who collect the biomass. Usually you go out and collect the firewood, etc., with all its attendant dangers. That's another story entirely. But they are the ones who burn substances for cooking and are most exposed to the smoke. And also they are the ones who have small children with them. So small children are particularly at risk and they can suffer developmental difficulties because of constant inhalation of smoke. And the figures are really staggering. In India, for example, up to 550,000 deaths a year are directly attributable to the use of biomass as a source of heat for cooking and for heating. And 6% of the total number of deaths. That's a substantial amount and is really a major health crisis in many of these areas. So the response to this, first of all, to try and regulate the use of these biomass as a source of fuel is very, very difficult because these often are the only things which are available to poor communities, and also they are traditional, and it's very difficult to break traditions of this kind. But what is being tried is to develop better, more efficient stoves, better ways of burning, so that, for example, when you burn wood or whatever, instead of it being partially burned and releasing compounds which are partially burned, the stove is designed so it is very carefully aerated, gets lots and lots of oxygen, and all of the available carbon is burned to carbon dioxide, which can be vented outside. And there's no toxic carbon compounds released as a result. that does another thing. It makes the stove very efficient in harvesting heat. So you don't have to use so much fuel. You only have to use a little bit of fuel, harvest all of the heat that you can. And that in itself is advantageous. And the last thing is that many of these stoves are made to be portable so that they can be moved inside, still vented to the outside, but they can be moved inside for cooking inside or for heating. And they're ultimately, as the country develops or as technology moves into these different areas, then people are going to be moved onto using gas or even better, electricity for their cooking. It's very difficult to do, though. If you read up a bit about it, there are some readings and there's also some videos for you, you'll realize that these are traditional systems. Cooking over a fire is a traditional system, which has much more cultural importance as well as its utility for cooking. And people gather around the fire. We all love to gather around a fire and talk and while you're cooking or whatever. It's hard to remove that social welding away from a community and expect them to gather around an electric stove. It just wouldn't happen. Okay, so that's indoor pollution. Indoor pollution is a tremendous problem worldwide, but even greater problem is outdoor pollution. And there are, first of all, even in the absence of human beings, in the absence of technology or anything else, there are natural sources of pollution. And first of all, volcanoes can contribute a huge amount of sulfur dioxide and other gases to the atmosphere. They also can produce vast quantities of very, very fine volcanic ash. Now, volcanic ash is not really ash. Volcanic ash is actually particles of pulverized magma, of pulverized rock. And it's silica, it's very rich in silica. And if inhaled, it can be extremely damaging to the lungs. The second source, of course, one that we know very well in the United States is wildfire. Wildfires contribute exactly the same things that a wood fire does inside a house, but in huge quantities. And the wildfires may pollute vast areas, as we learned last year when New York was blanketed by wildfire smoke from Canada. The last, you may not even think of as being a pollutant, but this is dust. And dust is composed of very, very fine particles. And dust is, in general, very fine sand. That is also silica, the same as we saw from the volcanoes. It's very fine silica, which can definitely be inhaled and cause health problems. And dust plumes can move very, very far from their origin. For example, this is Africa. This is the bulge of Africa there, the west coast, and the northwest coast. And this here is all dust from the Sahara Desert. And in summer, there's prevailing winds which lift dust every 2 to 5 days. There is this dust, effectively a dust storm, which moves out across the Atlantic. Now, a lot of that may settle into the Atlantic, but it actually can spread very, very far around the globe. And this dust particles are found as far away as Hawaii from the Sahara. So I think I've got another slide in a while to show you. Okay, so here this is a Saharan dust storm in 2020. This is one of the largest, actually, on record. There is concern that with global warming, these dust storms are going to increase. And you can see here, this is the Saharan dust plume here moving over the Caribbean and Central America. but it impacted very heavily in Texas. This is Houston. And this is just a cloud of very, very fine silica, potentially extremely damaging when it's taken down deep into the lungs. But there is something else to say about this. And that is, it has been discovered, I mentioned Hawaii. In Hawaii, the soils there are very, very poor in phosphate. And this is a limiting factor for the forests and the vegetation in Hawaii. There's so little phosphate. But they derive enough phosphate just from these dust storms coming all the way either from Sahara or sometimes from the Gobi Desert in China, and that provides enough phosphate to maintain the forest in Hawaii. It's quite an extraordinary thought, but it is true. So these dust storms actually have an ecological function that they perform, an ecological service that they perform. If you want to read more about the dust storm, I've given you a link there. It's not required. Okay, so those are natural forms of pollution. But of course, we must turn our attention to the major man-made sources of pollution. And there are numerous of these, but here are three which I think are of particular importance. The first, of course, is industrial and domestic use of fossil fuels. And that is especially use of fossil fuels like coal and low-grade oils, which contain things like sulfur, all sorts of compounds that are not useful, but which get partially combusted and released as very toxic compounds into the atmosphere. The actual extraction of oils and of gas, like methane, in itself is very damaging and is very polluting, because methane leakage from gas wells and things like that is enormous. And methane is a greenhouse gas. It's a greenhouse gas with great potency. It is greater greenhouse gas potential than carbon dioxide. And as we reduce the amount of carbon dioxide into the atmosphere, the relative importance of methane becomes greater and greater and greater. Now, when we look at the mortalities worldwide, 61% of deaths due to pollution, due to air pollution, are due to the use of fossil fuels. They are hugely, hugely important. The next group, of course, again, depending on fossil fuels, but these are vehicular sources. These we call stationary sources, and these are moving sources of pollution. And the use of vehicles of all sorts, not only in motor cars, aircraft, boats, cargo boats are contributing a huge amount to global pollution, for example. And these, again, are dependent upon fossil fuels, and they release a whole slew of different pollutants: carbon monoxide, carbon dioxide, all of the nitrates, all the nitrogen oxides, abundant VOC, volatile organic compounds. And I will also mention lead. And I'll have we need to just think about this for a minute. Lead was included in fuels for cars, for vehicles, because it improved the function of the efficiency of the engines. And unfortunately, that meant that a lot of lead was spewed out of tailpipes. And this had a huge effect on children's development, especially neurological development. Lead is extremely toxic. And I'll have another word to say about that in a minute. The third major source of pollutants is agriculture. And agriculture, first of all, releases a huge amount of nitrous oxides of various kinds. And that is because of the use of high nitrogen fertilizers, which are broken down in the soil and release oxides of nitrogen. Second of all, it's the release of things like pesticides and herbicides. They are inefficiently applied, and a lot of it is volatilized and ends up in the atmosphere. Thirdly, is cattle produce a large amount of methane as part of their digestive process, and they belch it out. And they don't fart it out, they belch it out. There's always people are talking about cow farts being so important. It's not, it's their birthing that is important. They do produce a lot of methane, and it has a measurable effect in the atmosphere. And lastly, of course, farming is a messy business, and it produces the farm fields may be burned in many parts of the world. This is the equivalent of wildfire smoke, burning of agricultural fields. And also plowing everything produces dust. So these are three major areas of human or anthropogenic. That is a word you need to know. Anthropogenic means derived from human beings. Okay, so here's the one solution situation that you probably already know well. And this is the occurrence of smog. Now, smog is pretty much characteristic of any city anywhere in the world, but in some places it is far worse than others. And smog has particular characteristics to it. It is visible. That is the first thing, and is visible for some particular reasons. It's a haze that is produced largely from particulates, but associated with it, depending on its origin, may be different gases. And some of those gases are often very toxic. And it largely arises from industrial sources, from industry, smokestacks, things like that. And then also, of course, from motor vehicles as well. It may be exacerbated by natural sources such as wildfires, contributing to the smog as well. And where domestic use of fossil fuel is not carefully controlled, domestic use may also be a major contributor, especially in areas where, for example, they use coal for cooking and for heating. So these result in the release of a whole range of different kinds of compounds. The first of real importance is sulfur dioxide. Again, sulfur dioxide actually attracts water vapor, forms droplets, and those droplets form a sulfuric acid. Next, of course, are particulates, soot. I've already talked about these particulates are derived from partially burned compounds, which the particles of soot themselves are extremely toxic. And this sulfur dioxide, the sulfuric acid produced in this way can have wide-ranging ecological effects, quite apart from the health effects of breathing this in. At times, this has resulted in pollution of lakes and rivers to such an extent that they effectively become sterile. The pH drops so low, the acidity becomes so great that life cannot be sustained. This is a problem because sulfur dioxide, soot, all of these things can be exported from their source. So you may have a state which is producing a huge amount of sulfur dioxide, which is then exported to another state where the effects are felt. And so what you end up with is one state, either a state in the United States or a state in terms of nations, may have to fight with another nation to get them to institute regulation because they feel the effects of it. The vehicles also produce particulates of partially burned fuels, but they also produce prodigious amounts of carbon monoxide and nitrous oxide, which is NO, and various other oxides of nitrogen, but this is of particular importance, as I'll show you in a minute. It released lots of hydrocarbons and lots of volatile organic compounds. So all of these things combined together just on their own, slewing around in the stew, would be dangerous just by themselves. But there's something which exacerbates their health effects. And that is when I take all of this mixture, this stew, and I bake it in the sun, something else happens. Sorry, let me go back here. These are all called primary pollutants. They are pollutants just on their own as they are released. But when we start to cook them in the sun, we start to produce other compounds, and those are called secondary pollutants. And this is a photochemical effect. And there's a specific situation called photochemical smog. And this is how it arises. First of all, you remember to take note of the nitrous oxide released, particularly by motor vehicles. Nitrous oxide released into the atmosphere comes into contact with oxygen. And when the sun bakes on it, it actually causes it to break up, recombine, and form nitrogen dioxide. And nitrogen dioxide has a distinct orange-yellow color. And that is what we're looking at here. In the background here, I have a picture of a smog situation. And this orangey-yellow tinge to it is caused by the nitrogen dioxide. So that in itself, nitrogen dioxide is extremely irritant and it's a bad pollutant. But when this photochemical process occurs, it results in the production of ozone. And ozone at this level, where it comes into contact with biological material, with living things, ozone is extremely dangerous. It is a potent irritant. It causes lung inflammation. So we've got two things here, nitrogen dioxide and ozone, operating together. People are breathing them in. And this is a dangerous combination. So nitrogen dioxide, that's what gives smog its color. It increases this photochemical reaction, increases the levels of ozone at ground level where we can breathe it. And in addition, remember, this is combined with all of these things. It's combined with the particulates and everything else that have been produced to produce the initial smog. In addition, I just mentioned this is that smog also produces these compounds here. They're called PAN, P-A-N, peroxyacyl nitrates. You don't need to remember that, okay? But these are important. They don't affect us very much. They don't affect animals very much, but they're very potently toxic to plants. And where smog begins to impinge on agricultural land, they can actually substantially reduce productivity. So it's not only animals that suffer from the pollutant effects, it's plants as well. So smog, the formation of these smogs, whatever kind they are, is very dependent on the weather. They are very easily dispersed by wind and diluted by wind. So they usually occur when in still weather, but they are especially prominent when there is a temperature inversion. I told you before, as we ascend in the atmosphere, we go from the surface up towards the stratosphere, the temperature drops. It gets colder and colder and colder. But there is a special weather situation close to the surface which can arise. Cold air is dense, it is heavy. And where it can be, where it's produced, like in winter, for example, in fall, and it can seep into like a valley or any enclosed area like that, the cold air can accumulate at the surface and displace warm air above it. So we have a cold layer at the ground and warm air above it. So that's why it's called temperature inversion. But that boundary between the cold air and the warm air above is a very profound boundary. And it can contain pollution. It prevents the pollution from being diluted. So the smog begins to accumulate underneath the temperature inversion. It's also profoundly affected by geography. So, for example, if you've got surrounding mountains, or if you've got a mountain on one side which stops the movement of air, the smog can accumulate there as well. Now, as I pointed out, it's particularly common where things like coal are burned, but it is also very common where cars are numerous and where cars are not advanced technologically. As a result of the effects of smog, especially through the 1960s, 1970s, there were movements to improve the functioning of car exhausts so that they now screen out many of the pollutants. And smog is becoming less common in developed countries than it used to be. But here's an example. This is China. This is an example of the importance of weather. This is China on day 1. This is the same view on day 10. And this is purely due to 2 things, and that is the still weather and a temperature inversion, which has accumulated the smog against the ground at ground level. So these, as I said, these smogs can also be exacerbated by natural events like wildfire. And this is us last year. This is New York last year. And this was the famous Canadian wildfires. The smoke plume stretched as far down as Virginia, which is south of Washington, D.C. We had it very, very badly here in New York. Now, just for those of you who are here, I just want to point something out. What do you notice? First of all, the color. The color is actually due to nitrogen dioxide. The obscurity is due to the particulates that you're seeing that are suspended in the air. But I want you to remember what it smelled like. When you stick your nose out and you sniff, what do you smell? Well, you say, oh, I'm smelling wildfire. I'm smelling smoke. What are you smelling when you smell smoke? You're smelling volatile organic compounds, which are present in the air. So there you have, here you have all of the combination of all of the really bad pollutants. Wildfire smoke is extremely dangerous and causes a tremendous number of health effects. So here, talking of smog, in the late 19th century, this is a painting by Claude Monet, a very lovely impressionist painting of the Houses of Parliament on the Thames River in London. But it's actually, look at the orange glow and tell me what that orange glow is. In fact, if you look at the painting carefully, you'll realize something. The sun is actually quite high in the sky. It's not close to setting. It's quite high in the sky. It should be bright daylight. Instead, there's this orange pall hanging over the city. What is that orange pall? It's smog. The orange color is due to nitrogen dioxide, and the smog is due to the presence of nitrogen dioxide together with particulates and everything else. And London used to be famous for these smogs. They call them pea soup fogs, and they were a combination of both natural fog, just water droplets in the air, but then with all of these pollutants stewed into it as well. And they called them pea soup fogs because they were they could become almost impenetrable. So I'll tell you about one. This is one of the most famous. It's one of the last ones that occurred. And it was so drastic. It had such disastrous effects that it led to complete reform of the laws regarding emission of material into the atmosphere in Britain. And this occurred in December 1952. It was very, very brief on the scale of things. It was only 5 days, but there was an intense temperature inversion. London lies in a shallow valley, the Thames Valley, and there was an intense temperature inversion above it, which capped it and effectively sealed the atmosphere off. And this very, very, very dense mixed fog and smog formed. And it was one of the major sources of mortality. In fact, not counted in the figures that I'm going to show you, but overall, there were many, many car accidents, and especially pedestrian accidents, because people simply couldn't see. They couldn't see through the fog. Even at midday, it was dark. There were two sources, and this is really important. The first was industry, and the second was domestic. Many, many homes used coal, both for heating and for cooking. And they used, this was after the Second World War. Britain was suffering extreme poverty as a result of the war. And people were reduced to using extremely cheap coal, which was very high in sulfur and which simply didn't burn well. It released tremendous amounts of soot and other compounds that we've talked about before. The second source was industry, of course. They were also very largely using coal, and especially for the generation of power. There were numerous coal-fired power stations in London itself, belching out results of burning to generate power. So this all contributed and produced this disastrous smog, which, by the way, was a photochemical smog as well. And they worked out afterwards that these extraordinary amounts of substances were being belched into a relatively small area of the Thames Valley, 1,000 tons of smoke particles per day. A ton by the NNES, it's a metric ton, and it's about 2,205 pounds. It's a bit over an imperial ton, which is 2,000 pounds. 140 metric tons of hydrochloric acid per day, 14 tons of compounds like fluorine. And these are important because they produce, they are themselves extremely irritant. Things like, think of breathing in chlorine from a household bleach or something. That would be what it would feel like to be breathing this kind of substance in. It produced 370 tons of sulfur dioxide, and that would be converted to 800 tons of sulfuric acid. This is per day for 5 days, that this all accumulated. This was disastrous on many. It had a huge economic effect. People simply couldn't get to work. The buses couldn't run. All of the taxis couldn't run. All of those sorts of things. There was a huge economic downturn in London as a result of it, but that was the minor part of it, because it resulted in thousands of deaths. So here is, this graph shows you the number of deaths per week. And this little black block here is the event itself. Now, this is to the Great Smog here for 5 days, but these are the effects afterwards. But immediately afterwards, there was a total of about 4,000 deaths. And then, so those people are people who died of asthma attacks, of bronchitis, of pneumonia, of all sorts of respiratory illnesses, as well as heart attacks and strokes in the immediate aftermath of the event. Then for months afterwards, people who had started to suffer really serious illness during the smog began to die themselves more slowly. A total of 8,000 deaths before the turn of the year, before 1953 ended, and before the end of February 1953, and in total, it was about 12,000 estimated at that time. There have been modern studies which have put the deaths somewhat higher at about 15,000, just from that 5-day event. So this had the immediate impact of people demanding that legislation be passed. The use of coal and of wood and of peat as household heating and cooking was banned in Britain, especially in the cities. And instead, they began to move in gas into households so that they could use gas instead. They put in very, very strict industrial standards, and they began to close the power stations in the city itself. And they also began to phase out the use of coal as a source of fuel for power stations. And all of this has resulted in these smogs now becoming extremely rare in Britain and in other countries. Other countries followed suit because the other countries also had similar problems. So here I'm showing you, this is from a couple of days ago, and these are the most polluted. These were rated as the most polluted cities. I think this is for 2023. This was released, as I say, only recently. You can see that worldwide, there are still many places which have extremely hazardous pollution levels. Here is a scale up here to show you. This here is the top, up here, extremely hazardous. And look here, I've only put here the top 15 cities in the world. And you can see it here, 1, 2, 3, 4, 5, 6, 7, 8, 9 of those cities, 9 of the 15 have hazardous air pollution. The others have severe air pollution. And all of these are contributing to high mortalities and high amounts of illness in these cities. Along with that, just think of reduced efficiencies, reduced economies, et cetera, as well. And all of these places, these really, really bad ones, have some things in common. Many of them are still dependent on coal and wood and biomass for power generation, industry, and for home use, for cooking and heating. All of them have rapidly expanding industry and industry which is not particularly well regulated. All of them have those industries close to the cities and often interspersed in between urban areas. They're not isolated and far away, where their pollution could be dispersed or diluted before it reached the city. Instead, they are sited right in the cities. The pollution is immediate to the populations. They have very high population densities, and many of the people there are extremely poor and are clustered in informal settlements, and where they are entirely dependent, not on electricity or gas or anything, but entirely dependent on things like coal and wood and cow manure for their fuel. All of these things are combined to produce a situation where air pollution is a major health concern and a major contributor to mortality. Here's a very recent picture. This is of India and of associated countries. And again, have a look here. Here's the scale down here. And you'll see that for much of India, the air is actually between unhealthy and hazardous. And in India, this is such a huge problem that it actually produces about 2,180,000 deaths a year due to outdoor pollution only. That's not including the indoor pollution that we've talked about before, which is about 500,000 a year. And this figure here is a quarter of the total number of deaths in India due to pollution. So this is a substantial amount. And it's a quarter of the total number of deaths due to air pollution worldwide. So this is just a huge economic burden as well as a societal burden on the people of India. A similar situation pertains in other countries as well, especially if those which are rapidly developing, rapidly advancing technologically, where regulation has not caught up. Regulation and technology have not caught up to the requirements of reducing air pollution. In China, These are thought to be gross underestimates. 1 million people per year due to outdoor pollution, but another million due to indoor pollution. And that is largely because many areas use coal inside households. So these are huge, huge problems for the human population worldwide. But in developed countries such as the United States, legislation has gone a tremendous way to reducing the burden. We, in the United States, first passed regulations as the U.S. Clean Air Act, the CAA, in 1970. It was promulgated in 1967, but it was passed in 1970. And this act regulates industry. It strictly regulates the emissions from industry. And it also sets future targets so that industry can phase out systems and move in new systems which are more efficient. It also sets strict household pollution standards. For instance, you can't, it reduces in cities, institutes regulations for what you can burn in a fireplace, etc., things like that. Very importantly, it regulated the amount of pollution that could emerge from the tailpipe of a car. Now, this was largely the toxic gases, such as carbon monoxide and the nitrous oxides produced by the tailpipe. And it also regulated the heavy metal pollution. Now, this I referred to before, so this is like a separate little story. Notice that the Clean Air Act here is not regulating carbon dioxide. It is regulating noxious gases that are being produced by cars. And to remove those, industry was required to reduce those. And their response was to develop the catalytic converter on the tailpipe. And the catalytic converters work extremely well. There was a problem. And that was that much of the gasoline used in the United States contained lead. Lead in itself, a very bad pollutant, but a very difficult one to regulate because it improved the efficiency of engines. But then the car manufacturers discovered that the lead was destroying their catalytic converters. And so they had to, the response was that the car industry itself agitated for regulation of lead and other metals in fuels. And so lead was largely banned from fuels. It can still be used on farms. It can still be used on motorboats, which have a simpler engine than a car engine. And it is also used in aircraft as well. So there are some sources of leaded gasoline, but overall lead has largely disappeared from usage in fuel. Now, I said that what this did not do was heavily regulate greenhouse gases emerging from vehicles and fossil fuel use. That was the responsibility of a separate set of legislation called the Corporate Average Fuel Efficiency Standards, the CAFE standards. It's the acronym. And this was introduced in 2009. And this has required a reduction of greenhouse gas emissions from vehicles in response to the worries about global warming. So these acts together have had huge impact. This is just for the United States, but it applies, similar things apply in developed nations elsewhere. And here, for example, don't worry about the details of just look at the trends of the graphs. The bar graph shows you vehicle usage in the United States. We use cars more and more and more year by year. But look at the volatile organic compounds released from tailpipes of cars. And look, you can see here, there's an exponential decrease. And this is due to regulation. This is not voluntary. This is because car manufacturers were told, you must do this. And they responded by producing systems which became more and more and more efficient at removing these compounds. Just in general, again, don't worry about the particular details. These show for all of these different pollutants, sulfur dioxide, particulate matter, carbon monoxide, the nitrous oxides, all of them, once the legislation was passed to regulate them. This is the effect of the CAFE standards, by the way, as well. So the two things combined, Clean Air Act and CAFE standards, have produced a massive decline in emissions from vehicles. So, and this kind of summarizes it for you. So this is just carbon dioxide, okay? The Clean Air Act itself did have an impact on the amount of carbon dioxide released from cars. And you can see it here, this massive decrease here, but it remained stationary for a very long time. And these are actually, this is just exorbitant amounts of carbon dioxide. These are high amounts of carbon dioxide being emitted. But with the introduction of the CAFE standards, you can see that there's been a progressive decrease in the amount of carbon dioxide. Again, this is due to improvements in efficiency of the engine and efficiency of catalytic converters. So this I took today. This is our current air standards, air quality over the whole of the United States. Now, this needs to be talked about a little bit about. Air quality is something which is very carefully calculated. You can look up air quality for New York for today. You can look up air quality or air quality for the whole country, for different areas of the world. If you want to, you can go to the EPA, Environmental Protection site, and the Environmental Protection Agency site, and you can look up all of the air pollution information, not only for the United States, for the rest of the world as well. But here it is for today. In the yellow, this yellow here indicates that these are areas with fair standard of air. And these actually, a lot of this at this time of year, in actual fact, is very fine particulates. And I want to give you a second to guess what those very fine particulates would be. Where are we? We're in spring. And a lot of this is actually pollen, which for people who are allergic to pollen, of course, is a huge problem. But in general, you can see that the quality, the air quality for almost all of the United States is extremely good. It's extremely good. It's not always that good, but on this particular day it is. And that is largely thanks to the Clean Air Act and to the CAFE standards, which have so strictly regulated. I want to tell you one thing though. Industry hates those standards. Corporate America absolutely hates those standards because it requires them to invest so much money in adhering to them. And they are under continual threat. So keep your eyes open and be ready to defend the standards, because it's for this reason that the mortalities and the amount of illness due to air pollution in the United States has fallen prodigiously over the last 30 years or so. You can look up the air quality index. You can usually see it, find it in the paper. You can find it easily, find it online. Here, remember I showed you here, the yellow here. That is this here, and it's just saying that this is moderate air pollution. The air quality is largely acceptable. If you're allergic to pollens, for example, maybe you want to wear a mask, or you want to take an extra dose of your antihistamine or whatever. But the rest here, these do occur. And we were right up here last year during the episode when the Canadian wildfire smoke impinged on New York. You can look up in your air quality index, it will tell you. This was for yesterday for New York, and you can see it tells you each of the pollutants that we've talked about. Ozone, here it is here. This is nitrogen dioxide here. Here, these are particular PM, this is particulate matter. These two are separated because it's larger and then very, very small. But we don't need to worry about that. Sulfur dioxide here, which is usually from industry. It's excellent. There's no sulfur dioxide. And carbon monoxide, that is largely from motor vehicles or from industry, but very, very little. Yeah. So this is good news. This is also a success story. And this is a success story which needs to be exported to countries which are still suffering from massive air pollution. So here, just to finish off, to tell you, this is what the Clean Air Act prevented. These figures here, if the Clean Air Act was not in operation, these would have occurred. We would have had close to 250,000 people die from particulate matter in the atmosphere. We would have had 180,000 cases of bronchitis, which never occurred because of the Clean Air Act. We would have had more than 2 million cases of asthma, which would have been very serious, which are not so serious because of the Clean Air Act. These things actually work, and it's worthwhile paying attention to legislation and to what your legislators are doing in order to ensure that not only that these are maintained, but that they are improved on as time goes by. Okay, so that's it. There are several short but really interesting videos for you to watch, and there is also a student worksheet, but I don't think that you'll find it particularly difficult. And I will see you again next week. Thank you.